Okay, so we're ready to start the last section, 7.3, Bonding in Metals. Chapter 7 and 8 go closely together, so please don't forget the things that you're learning here. So, metals. Why do we use them the way we use them? How do we improve their properties? This is all kind of areas of chemistry. And when we make metals better, we're actually making an alloy. And we can make an alloy of iron by adding carbon, and we end up with what we call steel, which would increase its malleability, ductility, and it would improve its resistance to rusting and change its melting point, which is kind of interesting, at least to me. So how can we model metallic atoms and ions as well as metallic bonds? And we do not think of them as attached to a particular metal atom. Those valence electrons are kind of floating around. They're associated briefly with all sorts of different nuclei of the metal. And so they are considered the nucleus, and the core electrons are considered kind of a cation that's closely packed. And then those valence electrons are rather free to move around that nucleus. So it is not a neutral atom in the center. Valence electrons of atoms in pure metals can be modeled as a sea of electrons. So all those electrons are actually available to any other metal atom as well, and they can move in a particular direction, which allows metals to conduct current. So the valence electrons are mobile and drift freely from one part of a metal to another. And again, that's how you conduct electric current. That's not your first Easter egg, by the way. Metallic bonds are the forces of attraction between freely floating valence electrons and the positive charged metal ion. And this is what holds your metals together. And it actually gives some very interesting properties to metals. And so those properties, one of which is they're good conductors of electric current because those electrons can flow freely. So if we have an electron entering the metal at one end of a long wire or a bar, an equal number of electrons will leave at the other end. And so it'll go from one end to the other end. And it's not that one electron that started on the left, let's say, and goes to the right. It's actually one enters on the right, a different one leaves on the left. So that's kind of interesting to me. So metals are ductile. So your first thing that I want to see in your notes is the definition for ductile. And it is that they can be drawn into wires. Not that they can be hammered into sheets, that's something else. But the first one I want to see in your notes is the definition for ductile, which means they can be drawn into wires. They can also be hammered into sheets, and that's when you pull out a sheet of aluminum foil that's actually aluminum metal that's been hammered into a very thin sheet. And on the outside of the box, it'll actually tell you how many mils it is, and that's how many millimeters thick it is. So when a metal is subjected to pressure, either by a hammer or being forced through a die like it was in the previous slide, those electrons kind of act as a lubricant. They allow the metal atoms to slide past each other, the cation, the metal cores, and so then we can reshape it very easily. If we compare that to an ionic compound, if we apply the same kind of force, we will push the two cations together and the two anions together, and that will cause them to have a strong repulsion, and so they will actually shatter rather than slide smoothly past, because they would have to pass a ion of the same charge, which pushes them apart and makes them shatter. How are metals and ionic compounds different, and how are they similar? Well, both metals and ionic compounds form crystal structures. However, they have different configurations of those electrons, and the sea of electrons surrounding the metal cations allows the metals to be ductile and malleable. Ionic crystals will fracture under pressure. They're neither ductile nor malleable. We call them brittle. So the second thing I want to see in your notes is that ionic compounds are brittle. And if you don't know what brittle means, you need to make sure you have a definition of that. Alloys. Why are alloys important? Alloys are a mixture of two or more elements, one of which has to be a metal. And so you're going to need to know several. These aren't your Easter eggs, but I do want you to know the alloys of brass, and that is copper and zinc. You'll also need to know sterling silver. And sterling silver, the reason we use sterling silver is it's harder, it's more durable than pure silver, yet it's still soft enough to make into jewelry or tableware, and it actually is superior in terms of properties, even though it's not pure. Another one that I want you to know, so we've got brass, sterling silver, and now we're going to have stainless steel. And stainless steel is a mixture of a variety of things. One of them is chromium, and that's what gives it the shininess of stainless steel. Alloys can form from their component atoms in different ways. In fact, there's two types of alloys, and that's the last one I want you to have as your, so to speak, special thing. And the first one of those, and there's going to be two, are interstitial. And an interstitial alloy is one that is in the places between the atoms. And alloys are, I guess maybe they are actually in the spaces between the larger atoms. And why are alloys important? They are important because they often have properties that are superior to those of just the raw element. In the case of stainless steel, it resists corrosion. In the case of sterling silver, it is more, it gives us superior jewelry. The other one, which isn't on the slide, and I'm going to say it, so you're going to have to be responsible for it, is substitutional isomer, or substitutional alloys. And those are where something like brass would be an example of a substitutional alloy, because the two atoms are the same size and one replaces the other. And in stainless steel, iron and carbon's much smaller than an iron atom, and so it is an interstitial alloy. And so you might want to also remember or write down an example of each. So an interstitial would be carbon steel, and a substitutional would be brass, because the two atoms are the same size. So we're almost done. Valence electrons of an atom in a pure metal can be modeled as a sea of electrons. Alloys are important because their properties are superior to those of their component elements. You need to know the definitions metallic bond and alloy. The big idea here is bonding in metals we can model it as a cation surrounded by a sea of electrons. And the sea of electron models explains why the metals are good conductors of electric current and why they're ductile and malleable. And there we go. We're at the end of this unit. Thanks for listening. I'll see you in class.